Yeah. So thank you everyone for joining us for this presentation. My name is Faraj Zarei, and I'm from the CMG's UK office. This is really an overview presentation on CMG's capabilities with regards to our underground hydrogen storage. So there's going to be a lot of familiar concepts that we've used previously for other simulations. This is just a if you like, branding everything for this specific application. So there was a question yesterday, someone asking about the future of hydrogen. I just grabbed this from BP's latest report with regards to hydrogen. Currently, the use of hydrogen is virtually non-existent, and you have here two scenarios: rapid changes in terms of environmental impacts, which aims at keeping the emissions to below 2 degrees warm up, and net zero by 2035 and 2050. And you can see exponential growth in terms of market share for hydrogen. And this is in fact actually translates in terms of geographical effects as well. So you can see almost all parts of the world have to come on board with the idea of using hydrogen as a reliable source for energy if the fossil fuels have to be tailed down. So all of us are very familiar with the concept of gas storage. We have years of experience in terms of storing CO2 and methane, specifically for in the underground environments. It's widely accepted any sort of large-scale, long-term storage. The only viable solution is the underground storage. The four usual candidates are aquifers, oil deposits, gas deposits, and salt caverns. It's nice, actually, a recent paper from Tarkovsky gives a nice overview of the positives and, if you like, issues with each environment. While salt caverns are usually the least problematic, if you like, the only downside, the big downside is that their volume size are quite restrictive, and the caprock and can be quite delicate in salt caverns. So and the aquifers are not really reliable containers because the tightness of the caprock is usually much less compared to the usual environments when we have oil and gas deposits. So it's the only most of the time the only viable solutions are oil and gas deposits. Besides the usual characteristics in terms of geology, they are also a positive force in terms of having all the surface facilities there. So the cost of hydrogen storage is much less in oil and gas deposits. So that means we have a lot of experience with dealing in oil and gas environments. So now let's see what's different and what we need to look again when we're doing hydrogen in these environments. So in order to describe the behavior of the gas, especially when it's mixture, we need the equation of state, a reliable equation of state. And to define and to characterize the fluid, CMG solution is WinProp software. 2021 version of WinProp has added the hydrogen as a library component. So these are all standard library components. Every property of these components are known, and they can be used off the shelf in WinProp application. The choice of the equation of state in WinProp are Peng-Robinson 2 versions and SRK's 2 versions. Peng-Robinson 78 is usually the first choice in terms of the best choice, and that's widely used in the industry. We are aware that there are, if you like, better equation of states that can be used for hydrogen modeling. But the fact of the matter is that they usually come with a high computational cost. So far, all our clients that are using they have stick with the Peng-Robinson. Once you have the equation of state created in WinProp, if you have any lab data, if you have any mixture, any regression or anything need to be done, you can export the PVT into any of CMG simulators. IMX is black oil. It's not really designed for hydrogen storage. So we have the choice of GEM and stars. GEM is the compositional simulator, and stars is the K-value based. I'll go into the details of capabilities of these 2 simulators when it comes to hydrogen storage. So GEM, as I mentioned, is equation of state based, and it's been used for decades by oil and gas industry. So has developed many advanced physics and complex processes in models now that has been accumulated, if you like, over the years. For example, gas relative permeabilities, gas solubilities, diffusion, water vaporization. These are all processes that have been added to GEM over many decades, but they're all very much relevant when we're doing hydrogen storage as well. Over the next few slides, I'll give you a review of these capabilities in GEM and how they apply for hydrogen storage again. So we just had a detailed presentation on hysteresis. Just to remind everyone, the hysteresis accounts for the effects of the changing wetting and non-wetting phase when we're during the gas injection process. So the VAC processes, when we alternate between gas and water, is a typical problem when the hysteresis has a major effects. Over the past couple of years, GEM had added quite advanced options in terms of modeling hysteresis. And because hydrogen storage is by nature, again, is a cyclic process. You inject hydrogen, you store it, and then you reproduce it. The same physics also can be applied for the hydrogen storage as well. Gas solubility. Hydrogen is not the most soluble gas, but usually it's accompanied by other more soluble gases like CO2, methane. So it's very important that we take into account of the solubility. GEM models solubility primarily with the Henry's law now. So what it does is that Henry's law basically dictates that the fugacity of gas in water and the gas phase have to be the same. So GEM internally calculates the fugacities. So fugacity of the gas, any gas, directly comes from the equation of state, and GEM uses the Henry's law to calculate the fugacity in the water phase. It's a rather simple equation. You have the Henry's constant for any pressure and temperature, which is measured at the lab environment, and controlling the mole fraction of the gas in the water phase. These equation can be always maintained, and that controls the amount of the solubility. So as I mentioned, the Henry's constant is a pressure and temperature dependent. GEM can using these keywords can recalculate the Henry's law entered for other pressures. So the solubility calculation is always valid for different pressure ranges within the reservoir. And for more soluble gases like CO2, CH4, it has several built-in correlations that readjust Henry's constant, not only for the pressure, but also for the temperature and salinity as well. If you need more information, it's always GEM manual. You can have refer to GEM manual. Other more standard properties, obviously the aqueous gas phase density. We have the more, if you like, simpler case of linear calculations, or Rho-Chow, which is more advanced, taking into account pressure, salinity, and temperature when we are dealing with more complex physics, especially when it comes to like features like geochemistry are involved. The viscosity, usually the Keston correlation is the correlation of choice, because it's always maintains the consistency of the viscosity if you have pressure and temperature and salinity changes. And for the gas phase density and viscosity, the density of the gas is coming directly from the equation of state. Most of the time it's Payne-Robinson, as I mentioned. And the GEM also has JST correlation, which maintains the viscosity, gas viscosities in the simulation. Another major factor when we are doing injections, especially if the injection pressure injection volumes are quite high, is the dry out effects near the injectors. So in such circumstances, the saturation around the injection well can dramatically drop, and that's controlled again by the fugacities of the water in the fugacities of water in water and gas phase. In this case, water has to enter into equation of state, and GEM will maintain this equation and will drop the and will take into account the drop in the water saturations due to the high rate injections near the injector wells. In terms of reactions, we have two types of reactions in GEM. I would say they're the chemical reactions, or they are most of the aqueous reactions, things like CO2 dissociation. They are instantaneous, and they're controlled by a chemical equilibrium constant. The other type of reactions are Arrhenius reactions. In this case, these are rate dependent, and if you like, the speed of such reactions can be controlled by frequency factors and activation energy, and you can speed up or slow down such reactions to match any lab data if required. An example of these Arrhenius reactions is we use it for like methanation reactions when you have methane and CO2 injected into the reservoir, and and that, sorry, when you inject CO2 and hydrogen injected into the reservoir and you produce back methane. I'll have an example later on to show on this one. The other type of reactions are mineral reactions. These are much slower, and you have dissociation and precipitation involved with these reactions. Because we are dealing with solid reactions, with solid components, they can change the porosity and permeability of the porous media, and that's obviously is more dominant if you have geochemistry in the model, altering the properties of the quality of the rock. The important, if you like, note on gem reactions is that it's all the reactions have to be in soluble phase. So if there's any gas to be that has to react, it has to be soluble in the water phase first, and then it can enter into the reactions. There will on my last slide we'll compare this to what stars can offer in this context. The other major point is the thermal changes, especially for the hydrogen injection. If again we are having the large rates, the Joule-Thomson effects can create large temperature changes around the injectors, or if there's a significant temperature differences between the injected fluid and the surrounding rock. This has to be, the temperature effect has to be accounted for. So GEM solves full energy equation, and which has sections regarding convection, conduction, and then heat loss to the boundary, overburden, underburden. Again, all these processes, all these details can be captured in full energy equation, and an accurate temperature prediction is possible using GEM. Here I have a quick demo of how this works in reality. So the scenario we're modeling here is we're injecting a bit of CO2 for a couple of months as a cushion gas into an aquifer. You can see there's is CO2 already in the reservoir, and you notice that it's what I'm showing is the mole fraction of water, CO2 mole fraction water phase. So CO2 is in the reservoir and is dissolved in the water. So there's we don't have any hydrogen and methane in the reservoir yet. So if we play this, you can see initial in this plot, the red is CO2 injected, is dotted, and then the CO2 that we produce is solid red. The blue is hydrogen injected, and the solid blue is hydrogen produced, and the green is the methane. As I mentioned, the methanation reaction converts the initial CO2 and hydrogen into methane. So you notice as you inject hydrogen, there's methane being produced in the downhole environment, and you can see the hydrogen sits at the top of the this structure. At the end of the injection, at the end of the hydrogen storage step, you can see there's quite a bit of methane sitting in the middle. More heavier CO2 still is in the back, and then on the top we have the quite light hydrogen sitting on the top of this anticline. So obviously, when you produce, you're going to have a quite high rate of hydrogen initially produced, and then the methane is reaches to the well, and at the end, you produce a little bit of CO2 at the end. And it's an interesting observation was that while methanation is usually considered to be a negative effect, so you obviously want to store hydrogen and reproduce the hydrogen with the least contamination possible. There are actually projects in Europe looking at converting hydrogen into methane, and the reason being is that currently the usual gas distribution networks don't have all the specifications required for high hydrogen content. So some operators are looking into using the methanation as an intermediate step until the gas networks are updated for more to be able to handle higher hydrogen contents. So the other, probably the most important factor in terms of hydrogen storage is the geomechanics. Hydrogen is extremely small molecules, and it can escape from the caprock once there's the smallest cracks or porous or permeability in the caprock. So so having an accurate and reliable geomechanic model is paramount for any hydrogen storage success story. GEM has full geomechanics available in GEM. It is available in GEM. You can do a simple one-way coupling where you have the fluid, the usual fluid flow running in the background, which sends the information to geomechanics module, and this is running on the side, and you can keep an eye on the geomechanics properties. Or the more robust and more accurate ways to actually engage these two simulators with each other. So the flow simulators send the information into the geomechanics calculations, which calculates the strain, stress, and displacement. These parameters will impact the porosity and permeability in the model, and eventually that can change the properties of the flow simulators. So let's have a look at the an example again here. We have a gas storage example here, which has two caprocks. If I start this animation, you can see we're only injecting at the top, is the bottom section of the lower reservoir. As we start injecting, the bottom hole pressure increases until there's the first crack in the there's a permeable block in the bottom caprock. Immediately after that, there's a gas escape from this smallest smallest permeable block, which cause a pressure drop in the lower reservoir. You can see the BHP is dropping, and this is the amount of the gas that has actually escaped. The gas starts to accumulate on the top reservoir, and at some point even the top caprock also fails, and we have the gas escaping from the both of the caprocks, which can be quite costly failure. So everything that I showed you so far was about GEM, but we can very much similar capabilities are also in STARS. For those of you that are not probably familiar with STARS, it's another CMG simulators, which shares many of the same features. The big difference being is that it's k-value based. So instead of putting the equation of state directly into the simulator, the tuned equation of state is used to create k-value tables, setting for stars, each component, the amount of at each phase at different pressure and temperatures. The major advantage of stars over GEM is that it has a flex well option, which is a fully gridded, fully coupled well bore model that works alongside the main grid. So the fluid flow not only inside the reservoir but also along the well bore can be monitored, and we can keep an eye on the properties of the incoming and outgoing fluid within the well bore. So this slide, which is kind of my summary and conclusion slide, is that stars is pretty much the same, offers the same capabilities. So everything that we can do in stars is also possible in, everything that we can do in GEM that I presented is available also in GEM. But the positive side of the stars is that it has more flexibility in terms of reaction definition. So here the reactions can can occur in any phase, and we have more controls over the reaction rate. So you can create a nonlinear. You can create third dependencies of the rate to the third components, which in an exponential way, which can be used for modeling processes like bacterial growth, which are exponentials. This can be closely replicated in stars, but at the moment not in GEM. With that, I think I'm at the end. If you have any questions, I will be more than happy to try to answer.
Thank you, Faraj, for an interesting talk on CMG capabilities in terms of modeling hydrogen storage, not to mention even using CO2 as a cushion gas. That's what Dr. Eric McKay mentioned earlier. So really happy that there are capabilities to help us to look at, clean energy resources and that kind of thing. So quickly, so one question, first of all, from Dr. Iraj Ashagi from the University of Southern California. Thank you for this information about new CMG simulator capabilities. Do you think storage of hydrogen is best if done in semi-depleted gas or oil reservoirs, or should one consider saline aquifers? I would think if the purpose is avoiding carbon production by switching to hydrogen as a fuel, the storage in and production from such hydrocarbon reservoirs may be problematic.
Yeah, that's a fair comment, but as I mentioned, the big, if you like, warnings if you're considering are that they not usually have a good sealing cap rock, and that can be a major impact because again now is very light and can escape the smallest cracks. So for now, storing the oil and gas reservoirs seems to be the more reliable choice. And again, because those fields have almost all the infrastructure already installed, so they should be much cheaper to use those options.
Okay. One question from Amin Saida. I believe he's at Canadian Natural Resources. Thanks for your presentation. I was wondering, with water vaporization option, how salt deposition and formation damage due to water vaporization is addressed in this process?
Sorry, the question again was...
water vaporization option, you have salt deposition and formation damage potentially due to that.
Correct.
And how is it addressed in the process?
Yeah, it's actually, if you start water, if you start vaporizing quite rapidly around the well blocks, then the concentration of salt will increase. That will lead into precipitation of halite, for example, and that will reduce the injectivity. That's another reason why a correct numerical model should be part of any design process, so we can do a proper analysis on what rates can we deliver without actually putting a reservoir in danger of such damages or caprock failures, so on and so forth.
Okay. So that's good. We finished the Q&A for Faraj, and thanks a lot from CMGL allowing you to showcase your capabilities in simulation of hydrogen storage. Thanks again.
Thank you for the opportunity.